Thank you very much for that kind introduction, and let me get started with my talk here. So I will talk about the history of surface science. I'm not a historian, so this is going to be a personal perspective. I was asked to prepare this talk for the 60th anniversary of the American Vacuum Society in 2013. And I've been active in this field for almost 40 years now, so at least I can cover a reasonable part of it. I'm not going to talk about a lot of things, and particularly not about chemistry or about catalysis, which in a sense is a shame because I won't be talking about Irving Langmuir or Kai Ziegbahn or Agnes Pakels or Catherine Blodgett or Linus Pauling or my good friend Joost Franken. But I'll be talking about a lot of other stuff, which is interesting also. So like I said, the AVS was founded in 1953 and has been one of the main conduits for meetings and communications and publications in surface science. It was founded in New York in 1953 in the Commodore Hotel. And you can see the nice ballroom photograph on the bottom right where the first meeting was held and where people gathered. It was a small field at that time for sure. I have a slide here where Walter Bratton, one of the inventors of the transistors, gave an address at the opening of the second conference on the semiconductor surfaces in 1959, and he says, "It disappoints me at this state of the art to see so many papers in which either one is working solely with the surface and which one can only measure the physics without any knowledge of what's going on chemically, or at the other extreme one is working with the semiconductor surface with which the physicist could not possibly tell you what the surface was like, or even what the body properties were like, paying attention solely to the chemistry. The hope of this field, of course, is that somewhere along the line we'll learn to do both the chemistry and the physics on the same surface at the same time, and from these results reach a new level of understanding of surface phenomena." Now, this has happened over time, and we'll show some of that. The Surface Science Division was founded in 1968 by Peter Hobson, Charlie Duke, and Robert Park. And in 1971, I believe Robert Park mentioned, surface science was definitely where the action was in both the physics and chemistry communities. The first Welch Award, the main award by the American Vacuum Society, was given in 1970 for the first time to Erwin Mueller, whom you see here together with Luther Preuss, the president of the AVS at that time, and Merritt Welch, for seeing the atom on the surface. But let's go way back to the pre-dawn of surface science with the discovery of the electron. So the electron was discovered in 1897 by J.J. Thomson, who received the Nobel Prize for that discovery, and you see the announcement of his passing on the left. On the right you see a book cover, A History of the Electron by J.J. and G.P. Thomson, G.P. Thomson being J.J.'s son. When J.J. discovered the electron, G.P. Thomson was one of the people who found that electrons behave like waves experimentally. And this was done in the experiment that you see here, which is a precursor to the transmission microscope, where we have an electron source at the bottom. The electrons go up and pass through a thin sample at 30 kilovolts or so. And then a photographic plate at the top records the diffraction pattern. You see here diffraction patterns on thin films of celluloid, where the rings are indicative of diffraction of the molecular structure of the celluloid films. This was also done, or in fact done earlier with low energy electron diffraction. And what experimentalists did here, Harry Farnsworth was one of the people to do that, was to record the intensity of the secondary electron current as a function of energy. So on the top left you see these curves of secondary electrons from copper with very pronounced oscillations on it. And today, of course, looking at a modern eye, we say, these oscillations are, of course, due to diffraction. But Farnsworth had no idea of diffraction. It was only in 1925 that de Broglie published his proposal that the wavelength of the electron is given by Planck's constant over the momentum. And not until 1926 that Heisenberger and Schrödinger come up with the wave theory of the electron as we know it now. The first really convincing diffraction experiments, as you see here, were done by Davison and Germer and published in 1927. Now, this did not happen by accident, actually. Davison and Germer had seen similar wiggles to Farnsworth, but had no idea what they meant. And the experiment broke down. And during the summer, Davison decided to take a break from it all and went to England, where he went to a conference in Greybridge and showed the wiggles. And to his astonishment, Max Born stood up and said, "Oh, these are the wave oscillations that de Broglie had proposed just last year." Now, Davison was completely unaware of any of that, and so he was rather shocked to hear Max Born utter those words. But Born explained it to him, and when Davison went back to the United States, of course, now he knew exactly what to look for, and very quickly he and Germer found experimentally, using reflection of electrons from copper single crystals, rather from nickel single crystals, these beautiful diffraction maxima that also occurred, agreed perfectly with the lambda equals h over p law, which wasn't a law, just a guess that de Broglie had proposed just a few years earlier. Lester Germer was really a pioneer in surface science and stayed in this field for the rest of his life. He was born in 1986, went to Cornell in 1917, worked at Bell Labs with Davison, was a World War I fighter pilot, and died in October 1971 doing what he did like to do best, which you see in the top left photograph, which is climbing. So he died in a climbing accident at that time. Many years, this is from a Physics Today article in 1964, he revived LEAD as late as 1960 when he constructed the first glass rear view low-energy electron diffraction screen, very much like we know today, but pretty much until that time people had to measure electron intensities with a Faraday cup or something like that. So it was really difficult, and nobody had ever seen a diffraction pattern before. But as you see here in Physics Today, in 1960 it became possible to see these diffraction patterns in real space for the first time. And it really provided a breakthrough for surface science, because now it became possible to see the symmetries and the reconstructions, etc., on surfaces very vividly for the first time. And this, of course, became a precursor to the low-energy electron microscope as we know it today.